Section: Introduction. In this section, we discuss how machine learning has evolved since the 1970s, yet the core idea of empirical risk minimization, ERM, remains the same. ERM suggests that we can reduce the loss for new data by minimizing it on a training set. In the past, when models were simpler, we could often show that good performance on training data would lead to good performance on test data. However, with the complexity of modern neural networks, this is no longer guaranteed. We propose a new framework for ERM that is better suited for today's large models and diverse datasets. Our motivations for seeking an alternative include: 1. ERM can be highly inefficient. 2. The concept of generalization in deep learning is not well understood. And 3. Improvements to ERM could benefit the entire field. Datasets have become much more varied. Previously, we trained on small, standardized datasets like MNIST or Shakespeare's works. Now, we train on vast amounts of data from the Internet, which includes both Wikipedia and various books. For instance, we used to train a language model on Wikipedia and then fine-tune it on Shakespeare, using different functions to represent their styles. Now, we use a single function for all Internet data, which cannot effectively capture the distinct styles of Shakespeare and Wikipedia, leading to noise that our machine learning framework should account for. ERM, using losses like cross-entropy or mean squared error, implicitly models the unique aspects of each training example through output noise. However, the data remains unchanged whether we separate it into different datasets or keep it together. If we can capture variability across datasets with different functions, we should also model variability within a dataset using function noise, rather than output noise. To tackle this issue, we introduce functional generative models, FGMs, where each data point comes from its own unseen function that fits it. Instead of looking for a single best function, FGMs consider a distribution over functions to account for function noise. From FGMs, we derive the Functional Risk Minimization, FRM, framework, where our training objectives are evaluated in function space. Our main contributions include the introduction of FGMs, the derivation of the FRM framework with a practical and scalable approximation, and a connection to the generalization of over-parameterized neural networks. We also present empirical results demonstrating the benefits of FRM across various experiments in supervised, unsupervised, and reinforcement learning. Section Summary. In this section, we highlight the limitations of empirical risk minimization, ERM, in modern machine learning, particularly with large neural networks and diverse datasets, and propose functional generative models, FGMs, as an alternative framework. FGMs assign a unique function to each data point to better capture variability and noise, leading to the development of the Functional Risk Minimization, FRM, framework, which we demonstrate through empirical results across various learning tasks. Section: Empirical Risk Minimization, ERM. In this section, we discuss empirical risk minimization, ERM. When using an ML framework like ERM, our goal is to reduce the loss on new test data. Typically, we focus on minimizing the loss on the training data instead. The best training objective relies not only on the loss function but also on the functional class and the data distribution. Often, ERM aligns with maximum likelihood, where we model the output based on a noise model. However, the loss function we choose may not relate to the data distribution, leading to suboptimal assumptions. Next, we explore Bayesian learning, which, like maximum likelihood, assumes a true parameter exists and includes a noise model. It also posits that this true parameter comes from a known prior distribution. This approach separates the inference of the output distribution from the risk minimization process. Consequently, the inference about the posterior becomes independent of the loss function, and we only combine them in the final prediction step to minimize expected risk. We then relate this to functional risk minimization, FRM. Similar to Bayesian learning, FRM clearly distinguishes between inference and risk minimization. However, FRM considers noise in the function space as the source of variability, unlike Bayesian learning, which assumes noise only in the output space. Like FRM uses a single parameter at test time, avoiding the complex integration found in Bayesian methods. In terms of related work, functional generative models, FGMs, treat each data point as its own task while remaining within a single task framework. This approach connects to multitask learning and meta-learning. Implementation-wise, FRM aligns more closely with studies that examine distances in parameter space or utilize implicit gradients. FGMs leverage multitask literature to effectively model noise in a single task context. We note that various studies emphasize the importance of function space in applications like minimizing catastrophic forgetting in continual learning and optimization in reinforcement learning. Information geometry offers a framework to understand the geometrical structure of distributions. In contrast, our work focuses on the stochastic nature of function space for modeling and learning. Several alternatives to ERM have emerged, especially in multitask settings, such as adaptive and invariant risk minimization. Other relevant studies address correlated label noise and aim to achieve flat minima to enhance generalization in supervised learning. Unlike these approaches, FRM incorporates per-point functional perturbations from the data distribution, rather than applying regularization on top of ERM. We also mention that some works propose per-point adaptations to customize models for specific inputs, which fine-tune an imperfect ERM model. In contrast, FRM treats per-point models as essential, leading to losses in function space rather than output space. Finally, we aim to draw conclusions about a distribution from a finite dataset. However, generalization requires assumptions. While much research has focused on finding suitable inductive biases for mappings, less attention has been given to questioning the assumptions about the uncertainty of these mappings. For example, minimizing mean squared error in image prediction assumes Gaussian noise, but actual noise is often more complex. Our approach, which we call functional generative models, FGMs, models each data point as originating from its own function, with the parameters being unobserved latent variables. Section Summary. In this section, we discuss the limitations of empirical risk minimization, ERM, and its variants, highlighting how they often rely on suboptimal assumptions about loss functions and data distributions. We introduce functional generative models, FGMs, as a novel approach that treats each data point as originating from its own function, allowing for a more nuanced understanding of uncertainty and variability in machine learning. Section: Modeling the arbitrariness of dataset definitions. In this section, we explore how dataset definitions can be arbitrary. A dataset implicitly defines what data belongs to a specific distribution, like a dataset of Boston houses sold in 2020, which excludes houses from New York or from 2005. Each of these categories has its own distribution, and using hierarchical Bayes, we can model them with similar parameters in a single function class. Moreover, even the Boston 2020 dataset includes various distributions, such as houses from different neighborhoods, months, or colors. These hidden distributions can introduce noise if not accounted for. Without specific information, we assume that each data point comes from its own distribution, leading to functional noise. This results in a hierarchical Bayes model where each data point's function is sampled from a learned distribution, representing functional generative models, FGMs. Next, we discuss what users need to provide a learning framework, a dataset of paired inputs and outputs, a function class, and a loss function. Unlike traditional Bayesian approaches, FGMs do not assume independent noise models, which may not align with user expectations. Instead, they rely on the user's confidence in the function class to accurately map inputs to outputs, while also accounting for uncertainty in these mappings. We also highlight that FGMs derive their strength from the function class. If the function class has specific constraints, the FGM will reflect those constraints in the probability space. For instance, if we use linear functions, the expected output given an input will also be linear. By employing FGMs with convolutional neural networks, we can create structured noise priors in image data. FGMs utilize structured function maps to build structured probability distributions across various models, including graph neural networks and probabilistic programs. Furthermore, FGMs assume a relationship between the output and input distributions. While this does not need to be overly complex, some highly expressive function classes, like multi-layer perceptrons, can lead to equally expressive FGMs in probability space. We formalize this in a theorem, which we prove in the appendix. Finally, we demonstrate that empirical risk minimization, ERM, for common objectives like mean squared error, L1 loss, accuracy, and cross-entropy can be viewed as a specific case of maximum likelihood within an FGM framework, where randomness is limited to the output parameters. We provide visual insights into how empirical losses relate to functional losses in output space. Section Summary. In this section, we model the inherent variability within datasets, recognizing that each dataset can represent multiple distributions and that functional generative models, FGMs, can capture this complexity by leveraging user-defined function classes. We also demonstrate that FGMs can approximate any probability distribution and show how empirical risk minimization, ERM, aligns with maximum likelihood estimation within the FGM framework. Section: Functional Risk Minimization, Learning in Function Space. In this section, we examine the supervised learning problem under the Functional Generative Model, FGM, assumption. Our aim is to minimize the expected risk by applying the FGM assumption and performing some mathematical manipulations. When we refer to the unknown probability distribution, we denote it as P, theta, which is fully defined by the data distribution P, x, y, and the function class f. The H cross-entropy operator is represented as H, P, Q, and we define Q underscore theta underscore star, theta, as the exponential of the negative expected loss between the functions f underscore theta and f underscore theta underscore star, normalized by z, theta underscore star. The normalization term z, theta underscore star, is the integral of the exponential of the negative expected loss over theta. To build our understanding, we note that the second term, which is the negative logarithm of z, theta underscore star, acts as a regularizer that penalizes theta underscore star, encouraging a sharper distribution. The first term promotes the alignment of two probability distributions in function space, P, theta, which is the unknown data-dependent distribution that does not rely on the loss function L, and Q underscore theta underscore star, theta, which is a class of distributions influenced by the loss function and the parameters used for predictions, but not by the labels. This approximating distribution becomes more likely as the function f underscore theta approaches f underscore theta underscore star according to the specified loss. Importantly, we do not need to know the exact shape of P, theta, which could be complex. We only need its projection onto a specific class of probability distributions relevant to our task. This is similar to empirical risk minimization, ERM, where to minimize the mean squared error, we only need the expectation of y given x, rather than the entire distribution of P, y given x. We aim to optimize the cross-entropy H, P, theta, Q underscore theta underscore star, theta, but we lack samples for P, theta. We only have pairs, x, y. We approximate this by computing the cross-entropy on P, y given x, based on the functional generative model. For a given dataset D underscore train, the FRM objective involves a high-dimensional integral under a nonlinear constraint, which is computationally challenging. To address this, we propose two practical approximations, a variational approach for language models and a Taylor approximation for models with many parameters, which is common in deep learning. In the variational method, we use a simple function class to approximate an intractable posterior. Our posterior is defined as P, theta given x underscore I, y underscore I, which includes an indicator function that ensures the predicted function matches the actual output, along with an exponential term based on the loss. We seek to learn an approximation Q underscore phi given x underscore I, y underscore I that is close to P, theta given x underscore I, y underscore I. However, The indicator function imposes strict conditions on the samples, and the output space can be vast, potentially reaching billions of dimensions. We note that these challenges can be managed for large language models, LLMs. We model the distribution of biases in the last layer as an independent and identically distributed Gumbel distribution, transforming the constrained integral into a log likelihood of a softmax. If we fix the other parameters, this approach recovers the cross-entropy objective used in modern LLMs. While modeling uncertainty for all parameters except the last bias is complex due to their large number, LLMs can effectively represent various functions with a large frozen core and minor adjustments, such as input prompts or low-rank adaptations. This allows us to model functional uncertainty in a computationally feasible way, resulting in a distribution for theta that incorporates both the adaptation and the learned structure. Section Summary. In this section, we derive the Functional Risk Minimization (FRM) framework from expected risk minimization by leveraging a functional generative model assumption, which allows us to approximate complex probability distributions using simpler forms. We propose two tractable methods for optimizing the FRM objective: a variational approach for language models and a Taylor approximation for deep learning models, addressing the challenges of high-dimensional integrals and parameter uncertainty. Section: Approximating the FRM objective by leveraging over-parameterization. In this section, we approximate the objective of the FRM by utilizing over-parameterization. We find that our system, represented by the parameters theta star, theta 1, up to theta n, is over-parameterized for the n independent constraints of fitting a single data point, xi, yi, using the entire parameter set theta I. This holds true even for a constant model where the output is simply a constant value equal to yi. Moreover, even smaller models, such as those with 10,000 parameters, may not have enough parameters to represent the entire dataset but can be excessively over-parameterized for fitting just one point. Therefore, similar to findings in the neural tangent kernel literature, we assume that a small change will suffice to fit each data point. We examine small changes, denoted as delta I, around theta star, where the magnitude of delta I is much less than 1. We then apply a Laplace approximation to our probability distribution, treating it as a Gaussian distribution. For regression, we note that the integral of the Gaussian under a constraint can be interpreted as the probability density function of yi, which is modeled as a Gaussian. When we compute its log likelihood, we realize that this approach goes beyond just weighted mean squared error since both ji and hf(L) depend on theta. This forms the training objective for our experiments. In the case of binary classification, the approach is similar, but we integrate over a half space instead of a hyperplane. To maximize the log probability of a function fitting a point, we minimize the Gaussian log cumulative distribution function of the signed distance to the decision boundary. Here, the signed distance, delta I, indicates how far the parameter theta is from the decision boundary. Notably, in classification, the optimal perturbation is not zero but rather a significantly negative value, suggesting that the parameter theta is well within the correct classification region. For multi-class classification, we integrate over the intersection of C-1/2 spaces, comparing each class with the correct class yi. Efficient integration in this context remains an ongoing area of research, with potential strategies including transforming the n-way classification into n-binary classifications or jointly linearizing the softmax of all incorrect classes. Section Summary. In this section, we approximate the FRM objective using over-parameterization, allowing us to fit individual data points effectively even with small perturbations around the optimal parameters. We derive the training objectives for both regression and binary classification by integrating Gaussian distributions, highlighting that the log likelihood computations depend on the parameters and the structure of the model. Section: FRM may do explicitly what over-parameterized ERM does implicitly. In this section, we discuss how FRM can explicitly perform what over-parameterized ERM does implicitly. We have noticed that neural networks can generalize even when they memorize the training data, which seems to challenge the traditional view of generalization in ERM that depends on controlled capacity. FRM assigns a unique latent model to each data point, meaning that for each input-output pair, we have a specific model that fits it perfectly. This allows us to transform a model into an over-parameterized hypermodel. Although the individual parameters are not directly observed in FGMs, the earlier Taylor version of FRM aligns with this optimization, where we seek parameters that are as close as possible according to a specific metric. While ERM aims to find the best fitting function from a set of simple functions, FRM focuses on identifying the simplest hypermodel that explains the data, in line with Occam's razor. We can think of this as finding the simplest set of parameters that fit the data, with simplicity measured by how close the parameters are to a central value based on a metric that reflects the relationship between the function class and the loss. This encourages all functions to be close to each other. We also relate this to research suggesting that ERM, when using gradient descent, may implicitly discover a function with two parts, a stable component and a spiky one, where the spiky part allows for overfitting. In this context, FRM explicitly searches for the smallest necessary adjustment for each data point. For our experiments, we adapted the Taylor approximation to work with neural networks. However, this involves inverting a Hessian matrix, which can be too large to handle in memory. We addressed this by using iterative solvers to reduce computational costs and only calculating Hessian vector products. We utilized JAX and the JAXOpt package for implementing implicit gradients. In our analysis of linear regression with mean squared error risk, we found that the classic ERM solution minimizes risk on the training data, which corresponds to maximizing likelihood under Gaussian noise. We expected ERM to perform well in this scenario but not necessarily in others. For FRM in linear regression, the approximations we used were exact, simplifying the objective significantly. Our results showed that while ERM performed slightly better with Gaussian noise in the bias, FRM excelled when the noise affected the slope, particularly in higher dimensions. We also demonstrated the versatility of our approach through an offline value estimation task in the mountain car domain. We aimed to learn a linear value function using a grid of radial basis functions and employed one-step TD error as our loss function. Both methods were optimized using stochastic gradient descent with a batch size of 256 and a learning rate found through grid search. We evaluated performance based on the root mean square error between predictions and actual values on unseen samples. We tested two arrangements of radial basis functions, a uniform layout and a denser one towards the center. Although the true value function has a discontinuity that might benefit from finer resolution, the non-uniform arrangement made the problem more challenging. Our findings indicated that FRM was competitive in the easier case and outperformed ERM by over 20% in the more difficult scenario. We believe that the TD loss is often affected by complex noise, which can hinder ERM when features are poorly aligned. Additionally, due to bootstrapping, the temporal difference error is inherently influenced by the function value, affecting the labels. Section Summary. In this section, we explore how functional regularization method, FRM, explicitly assigns a unique latent model to each data point, allowing for better generalization in neural networks compared to the implicit approach of empirical risk minimization, ERM. Our experiments demonstrate that FRM outperforms ERM, particularly in scenarios with complex noise and higher dimensions, highlighting its effectiveness in tasks like linear regression and value function estimation. Section. FGM-based VAE finds better representations within structured variations. In this section, we explore how FGM-based variational autoencoders, VAEs, can find better representations within structured variations. To understand when FRM outperforms ERM, we create a VAE using the MNIST dataset and two variations, colored MNIST and translated MNIST. We design a basic VAE with a multilayer perceptron, MLP, as the encoder and a convolutional neural network, CNN, as the decoder. We then assess the representation quality for both the basic VAE and an FGM-based decoder, where we model noise in function space. For the FGM approach, we train a small MLP on the latent representation while applying a stop gradient, measuring accuracy based on the latent size. In the MNIST dataset, where natural variations like orientation, translation, and color have been artificially removed, we observe some minor improvements. However, in datasets with color or translation variations, the gains from FRM are significant. This is because noise in CNN weights can effectively account for these structured variations. Additionally, previous research, such as deep image prior, suggests that neural networks are well suited for capturing real-world variability, making FRM particularly useful for modeling real-world data. Our results are illustrated in the accompanying figure.